Yeah, guys, we'll straight away start the session without any further delay. I would like to hand over the session to our beloved resource person, Mr. Tejesh Kumar Padda. Tejesh, please go ahead.
Yeah, good evening to one and all. Yesterday we are discussing about the LCD peripheral. We know I completed the theory also, full-fledged theory. And today I will show the implementation video. How can we dump the code and how can we connect the LCD to the FPGA? Okay. So this is the better peripheral. I think you are all or see this one LCD code very well. I will give the code. Okay. Don't no need to worry about it. See from the where did we stop there? Yeah. So we are declaring the first line. Of course, the 80 command will be declaring we have to access the first line. This is the set address. Okay. This is the set address for the first line, for the LCD first line. Okay. Just a minute. So this is the first line. And now now I am printing some characters yesterday. I'm already take the video. So this one, I'm already printed some characters. I'm already taken the video. I will display the video. Okay, no need to worry about it. I will display the how the hardware will be displayed. And same to so you have to follow the same procedure. Completion of code, you can connect the same hardware. Sir, but what about hardware pins, sir? Okay, code writing data is okay. Just like we have to give in the data 5D something, 12 clock cycles. Again, we have to give the 12 clock cycle, 2000 clock cycles. Next, we have to take another character, 8-bit. See, this is the 8-bit, 0101 and 001. That's it. Okay, just a minute. I will open the user manual. It's very helpful to you. Spartan 3. Yeah, user. Not in this window. Yeah. So suppose I want to display the A. See this one. I want to display the A characters. I think my voice is audible to you. Hello. Is my voice is audible? Can anyone please give me a response?
Yes, sir. Audible, sir.
Yeah. Thank you. Suppose I want to display the A character. A character. So the upper nibble is 0100. That means in binary. That means in decimal it is 5. So of course it is 00001. So now the lower nibble is 51. So you can directly write the 51 here. See, I'm directly writing the 51 here. So here we can take that 8-bit. You can select the register, select one. It will take, of course, it will take read or write operation. And of course, the register enable is also 1. Okay, then it will be the 3 commands will be activated here. See the 51. That means A. Of course, we will move to the next character. Of course, I don't know about what is this character. 62. We will check it. 62 means 0110. I think. Yeah, 60. I think it is small letter. 62. Yeah. 62, that means yeah, B, this small b. See this one. Of course, I am writing the wrong character here because I'm already changing the characters. Small b. Yeah. So this like the so you have to write the code like this. Okay. And your wish, you can continue the characters, or after 2000 clock pulses you can end the character, you can write the end module. That is also not a big problem. If your characters is over, then you can write end module. Okay, or you can continue that. So this is the overall Verilog code of this LCD. Okay, and of course this is the video output for the displaying the LCD. Of course, here we are implementing. Just a minute. Here we are implementing this LCD program. So we have to click on the program device. So follow the same procedure. Program device. Program. So coming to this package pins, just a minute. I forgot about this package pins. How can we connect the package pins, sir? It's very easy. According to my edgeboard, in the manual is there. Edgeboard manual is there. All of you. In the edgeboard manual, this is my user manual. So I'm following this one for the pins. So 2 into 16 LCD. Yeah. So this is my reference for the pins. See, I am connected the as it is pins of my tool. I will show it. I will show my pins. Okay. RTL open elaborated design background. So it will open to take some time. So today, I mean, of course, the after this LCD, we are discussing about the FPGA architecture. Okay, some internal architecture of FPGA. So of course, what is FPGA? So now we have to discuss about some theory, internal architecture of slice M, and of course CLBs, and of course some internal architecture is there, lookup tables. And tomorrow we are discussing about the ultrasonic sensor, and after tomorrow we are discussing about what we can call it as motor drive. I mean servo motor. Okay. Yeah. See, same pins. You have to see this manual. Same pins. See T3, P3, M5, N4. So same pins T3, P5, N11 clock pin is there. Okay. Of course, we are using the same pins, all of you. So this is my reference, and now we are done this code successfully, and I am getting this output. I think it is visible to you. Okay. Bracket. I mean close bracket. F. I mean we have to close it again. QBQ cap. So you can take the any kind of these symbols, no problem. See, for cap, I am taking this symbol. Cap symbol is also there in this one. Yeah. See, cap symbol. For the final one is the cap symbol. So I am taking this one. So you can display, you can write this kind of 8-bit code and you can display this one. So this is the total information about the LCD. Okay. I mean, for the now the LCD will be available, but it will be not visible for the camera. Okay. Of course, it is low brightness according to our there is no potentiometer here, so that's why it contains the low brightness. So that's why I will show the video output. Okay, I think it is the output is visible to you. I think this output is visible to you. Hello, see this left bracket. You have capital bracket something they are written here. Okay, I mean no problem. You can this is the code for the what we have to written here. See 5E. I mean, of course, don't see this one. Don't see this one. So you can see this one 5E. That means E means the final character. This is the E. See for cap E. Of course, this is F. So E and of course 5. That means cap. That is the cap. That's it. Okay. So we are deciding like that. So this is the total information about the LCD. Okay. So anyone have any doubts on the LCD, you can ask me. Otherwise, we will move to the FPGA architecture and design flow. All of you. Anyone have any doubt in LCD, you can ask me. Otherwise, we will move to the. So this is the total information about the LCD. Okay, successfully we are completed the LCD peripheral. You no need to worry about it. I will send the code. Okay, for your understanding, I will send the code. Then you can understand yourself how I'm write the code. Okay, for the detailed information, all of you. Not this one. Okay, the FPGA photo is missing. The architecture photo is missing here. But don't worry, I will draw the photo. Okay. Yeah. So now we will start the detailed theory about what is FPGA. Of course, some members are know the what is FPGA and what is the internal architectures. What are the internal architectures of FPGA? Contains there are how many blocks in that FPGA? Okay. So FPGA we can call it as a field programmable gate array. Of course, you people are know it very well. The definition, not the definition, full form. But coming to the FPGA means it's an hardware device for the verification, for prototyping also. Okay, it contains the logic blocks and different kind of logical circuits based upon the FPGA. Okay, there are different FPGAs in our world. Of course, they're manufactured by the different companies. Of course, there are different FPGA boards in this world. They are manufactured by the different companies. Of course, AMD, I mean, Xilinx FPGAs are manufactured by Xilinx, I mean, AMD company. Of course, they are D10 and FPGAs. They're manufactured by Intel company. Okay, but the theory is same. Yeah, FPGA. That means field programmable gate array. Okay, so you people are know about this theory very well. But these FPGA boards are reprogrammable. These FPGAs are reprogrammable and of course reconfigurable also. Reconfigurable. That means I will explain what is the reprogrammable and reconfigurable. Okay, suppose we are using the FPGA. We are using the one FPGA board here. Suppose, I mean, here our laptop, we are connected to the FPGA board. We are connected this one. Suppose I am dumping the, first of all, I am dumping the Verilog code FIFO. Now it acts like as FIFO. Now the entire FPGA board is acts like as FIFO. Okay. And next one, I am dumping the code of course, what we can call it as DRAM. I'm dumping the Verilog code of dynamic RAM. Of course, now the FPGA board will be acts like as DRAM. The previous FIFO code will be deleted. The previous FIFO code will be deleted. Okay, that is reprogrammable. That is reprogrammable. It will be that is reprogrammable and reconfigurable also. You can do many types of program for the same FPGA board. Okay, and of course, one more point I'm missing. Yeah, see the FPGAs, we can call it as they are volatile. The FPGAs, many FPGA boards are volatile. You know the meaning of volatile. If we remove the power, definitely the total data will be erased. Suppose I'm dumping the Verilog code of FIFO code, for example. Now the FPGA is acts like as FIFO. Okay, asynchronous FIFO. Now the FPGA is acts like as asynchronous FIFO. Suddenly suddenly I was remove the cable. So the entire data or code will be deleted. So the entire code or data will be deleted or erased, whatever it may be. Because of why the FPGAs, many of the FPGAs are volatile. Of course, many of the FPGAs are volatile. You need to check any kind of FPGA boards. Most of the FPGA boards are volatile. Okay, all of you. And of course, the next point is the FPGAs are faster than CPUs. Faster than control processing units. You people are know about it very well. The FPGAs are faster than CPUs. That means control processing units for the system. So you can definitely replace with you have to use replacing with CPUs. The FPGAs are eligible for the replacing of CPUs because of but why in the real time we did not use the FPGA boards for the system connection, for the monitor connection? Why did not we use it in real time for the replacing of CPUs? Because of the cost efficient. Okay, the cost efficient. The FPGAs are very costly the very cost equipment. Nearly one board will be 20 to 25,000. Okay, that's it. And one more thing is there for the FPGA. After the verification of on FPGA, after the verification on FPGA, then we will move to the chip fabrication process. Okay, suppose now I want to design one chip. Now I want to design one processor. Okay, now I want to design one processor chip. So we did not directly move that. We have to write the Verilog code. We have to write the Verilog code. Okay, then we need to check the, we need to verification. We have to do the verification, software verification using SV or UVM languages, whatever it may be. We have to do the verification. And after we have to do the hardware, we have to use the FPGA for hardware verification. Sir, but why, sir? Already we are done the verification here. Why we are doing again? We have to do the verification here for double verification. See, this is just a software verification. For the checking of the hardware, definitely we need to check the frequency. We need to check the frequency, of course, power consumption. So we need to check these kind of points for the hardware verification. Okay, we need to check these kind of points. And of course, after we will move to the backend flow. Backend flow means you people are know it very well. Floor planning, power planning. I mean, I will write it. Floor planning and power planning. Of course, placing and routing. And of course STA is there. And after physical design process. I'm writing step by step. Okay, I'm writing the step by step process. Physical design. After this one, we have to do the physical design verification. Okay, the design is completed in the one tool, but we have to do the verification again. And for the final one, we need to move the fabrication process. After this one, we need to move the testing and package. Okay, so these are the fully kind of backend tools. See, up to here, sir, but these are not available in Vivado. See, the FPGA is for only for front end only, for Verilog code, and of course for the simulation verification, and the FPGA, the Verilog Vivado tool up to here only. We did not check the that is not for the backend tool. For the backend tool, a few tools are there like Cadence. I know the Cadence tool is the very famous for this backend. Okay, of course, for the physical design verification, few companies are now doing the physical design. I mean, not all kind of MNC companies are doing the backend flow. Only few companies is there, like Microchip. I mean, only few companies are doing this kind of foundries. I mean, this chip fabrication process, like Microchip, Qualcomm, Intel, this kind of MS, of course, NVIDIA, top one, and TSMC. Of course, now one company is there, Mochip. And Mochip is also there. They are working on these kind of roles, floor planning, power planning, of course, STA and physical design. They are working on these three kind of roles, Mochip company. Okay, they are working these kind of three kind of roles is there. Okay, okay, I'm coming of the design flow. Okay, no need to worry about it because of this is the after verification of the hardware, then they will move to the backend flow. Okay, without hardware, we did not move to anywhere because of why? Suppose without hardware, I'm moving to the physical design. Of course, suppose without hardware, without front end verification, if you move to the chip fabrication, definitely they have definitely the chip contains the lot of bugs. I mean, if you are once you are done the fabrication process, is there any bug in that chip? Definitely we cannot rectify that. Okay, this is the mandatory rule. So that's why this kind of there are many kind of verification is there. Physical design verification, of course, design verification, hardware verification, FPGA prototyping. Okay, once if you done the fabrication process, any bug in that chip, we did not rectify that. That is the universal rule. Okay, once the chip is fabricated, Okay, we are working on one Snapdragon processor. Snapdragon processor. If you've done one mistake in this one, after suppose we are found one bug. We found one bug here. Bug means, I mean, any kind of error. After fabrication, see, after fabrication, this process, after fabrication process, I mean, after the fabrication is manufacturing. After manufacturing process, we found one bug, but we did not rectify that. We did not rectify this. We did not rectify that. So that's why for the placement trainings or any kind of these things, they did not take the engineers easily. Of course, you people are not very well. In the 1990s, I think one Intel, I mean, I don't know the company name exactly, but one engineer was done the mistake, but he didn't know about it. After the fabrication process, he sent the 300 chips to the clients, 300 ICs to the client. But the client was briefly checked that the 300 ICs was not working. Again, they sent to the company. The 300 ICs was not working properly. The client was given the complaint to the company. But nearly for the 300 IC cost is nearly 400 crores loss for the company. Okay, because of 300 ICs, of course, they're more valuable. Okay, we know the IQ phone. You people are, we know the who is that kind of clients. We know it. I mean, you need to know about it very well. Suppose there is a IQ mobile is there, but internally IQ mobile processor, they are using the Snapdragon processor. Snapdragon processor is there. Okay, the Snapdragon processor manufactured by Qualcomm company. Okay, it was manufactured by Qualcomm company. He is the client, and of course, he is the team, whatever it may be, company or team working for the Snapdragon processor. And he's the client. The mobile team is the client company. Okay, we want the 300 Snapdragon processor. So he was ordered from Qualcomm company. Okay. Yeah. So this is the total information about the FPGA and of course mini design flow. Okay. I was explaining the detailed information about the backend flow. I think you people are very understood something this was happening outside. And yeah. So in the FPGAs, are internally they have three main blocks is there. Three main blocks. Sir, what sir? The FPGA contains only the three blocks. No, the FPGAs are internally contains the many different blocks, but they have only. But we need to discuss about only three. Of course, in our human body, there are main. I mean, there are different organs, but of course, what are the main one? Brain, heart, lungs, whatever it may be. So we need to discuss about the main parts only. So just like this, the first one is CLB. The CLB means configuration logic block. So this is the important one and main one, configuration logic block. Of course, this is the main block. Okay, and the second one is input output blocks. Okay, input output blocks. Of course, the third one is programmable interconnects. Programmable interconnects. Okay, so these are the three main blocks in the FPGA internal architecture. Okay, so these are the three main blocks. Now I will explain the detailed information about the each block. Okay, so first of all, we need to know about the CLB. So configuration logic block. Configuration logic block. Yeah. So now all of you, please see this one. This configuration logic block. Okay, they did not contain the only definition. Yeah. Yeah, no need to worry about it. So the configuration logic block, they are internally consist of different blocks like lookup tables. Okay, they contain the lookup tables and of course flip-flops, muxes, and of course for embedded element, I mean these are the digital elements. Okay, these are the digital elements. Lookup tables, flip-flops, muxes, and of course latches also. Latches also. Yeah, configurable logic block. Okay. I'm writing the wrong name. Yeah, thank you. Yeah. So these are the internally consist the lookup tables, flip-flops, and muxes. Of course, the latches also. Because these are the digital elements. Okay, these are the digital elements. And now coming to this embedded elements like memories, registers. Memories and register, of course, internal memories is there, like DRAM, of course, DRAM memories and registers. Of course, the few more registers is there. So these are the embedded elements. Internally consist of the CLBs, and of course, other elements like fast carry logic. Okay, so these are the different elements that internally consist of the CLB. Okay. And the second one and third one is the input out block and programmable interconnects. We need to know about it, but I will explain the direct internal architecture of backend flow. I was very interested about it. No. Tomorrow I will explain about the backend flow of the program dumping. Now we will move to the, just a minute. Which one is there? Okay. Yep. So now we need to discuss about the types of FPGAs, and that's a good one. So sorry for the interruption. I mean, for the FPGA architecture, definitely I will continue. The few gaps. I mean, tomorrow I will explain the backend flow is there. Okay. But today the diagram is not available for me. I will explain the types of FPGA in this. I mean, I stopping this one because of the internal architecture. I'm stopping this one. Okay, the diagram is not available for me. Yeah. So now we are discussing about the types of FPGAs. Of course, there are the three types of FPGA. The first one is SRAM based FPGAs. SRAM based FPGAs, and of course the second one is anti-fuse FPGAs. Anti-fuse based FPGAs. Okay, of course the third one is flash based FPGAs. All of you. So definitely every FPGA board is undercomes to the each one of the type. Okay. See, now I will give the only one point without any kind of these things. See, the SRAM based FPGAs are reprogrammable. But volatile. So what is the meaning for this one? The SRAM based FPGA board. All of you. See, the FPGA board is reprogrammable. We can dump number of programs. We have to, it is eligible for to dump the number of programs. But if you want to remove the power, the code will be erased. That is called volatile. Okay. So this is SRAM based FPGA. All of you. This is SRAM based FPGAs. So now coming to this anti-fuse FPGAs. These are What? Just a minute. These are non-volatile. These are non-volatile, but one-time programmable. One-time programmable. Okay. So of course, if you remove the cable, definitely the code will be not erased, but it is only eligible for the one-time dumping. Of course, you people are understood what I'm saying actually. It is only for one time. This FPGA is only for one-time code. And of course, see, this is the disadvantage of this FPGA board. You need to know it very well. And this is the disadvantages of these type of FPGA boards. Of course, these flash-based FPGAs are now the trending FPGA boards. These FPGA boards are reprogrammable, and of course, non-volatile. Okay, these FPGA boards are reprogrammable and non-volatile, but the cost is too much high. This kind of flash-based FPGA boards. Okay, see, these SRAM-based FPGAs are manufactured by different companies like Xilinx or Intel company, and these anti-fuse FPGAs are manufactured by like Lattice Semiconductors. Of course, one more Cube company is there. And the flash-based FPGAs are commonly now this is the trending one. Yeah. This flash-based FPGAs are now the manufactured by Xilinx and of course AMD companies also, and of course Qualcomm. Okay. So these are the different kind of FPGA boards. But now we are using the Edge board. Now we are using the Edge Arctic 7 in the colleges. We know it very well. They are under comes to the which type? Can anyone tell me which type? This Edge Arctic 7 or whatever it may be. This Edge Arctic 7 under comes to the which board? I did not show to you. See, this is coming to the SRAM based FPGA. My board is reprogrammable, but if I remove the cable, definitely it will be the code will be erased. Okay, this is under comes to the SRAM based FPGA. And now, I mean, I saw the different kind of flash based FPGAs also. Okay, these antifuse based are very rare. I saw that many kind of flash based FPGAs also, reprogrammable and non-volatile, but is too much of high cost. Nearly 2 to 3 lakhs. Yeah. So this is the information about the FPGAs. Okay. No, this concept is yeah. No. So this is the today class. I mean, now I'm closing class off for that. This is the today class. Yeah, this is today for enough for that theory. And tomorrow I will explain the theory of back end flow of the Vivado. You know, I think you people are very well know about the front end flow. See, we are saying this now. We are writing the code and doing this verification. Of course, doing the verification and RTL analysis and of course synthesis implementation. After we move to the generate bitstream and hardware manager, we know it very well. But I will explain this back and flow of this tool, what happening of the internally. And you people are need to know about the internal architecture of the CLB contains the internal architecture component of LUTs. Of course, I'll zoom it. See, in LUT format. See, these are the lookup tables. Okay, LUT6. So this configuration logic block contains the different input of lookup tables is there. Okay, but I have some small doubt. Can anyone rectify me? I have a small doubt. In this configuration logic block, in this in FPGA board, we have 100 of configuration logic blocks according to our architecture. I will show the architecture tomorrow. In the FPGA board, we have 100 or thousands of so this is our FPGA board. I'm drawing the rough diagram. So we internally we have 100 of configuration logic blocks. See, each CLB contains the thousands of lookup tables with different inputs. Of course, LUT6, LUT3, of course, LUT2 is also there. LUT2 is also there. Okay, different. I don't know which LUT is there, which LUT is in which CLB. Okay, that will be based upon FPGA board. I don't know. Okay, LUT2 is here. Okay, LUT6 is here. That will be, we cannot decide, like, we did not decide that. Okay, that will be based upon FPGA board. So now tell me, how suppose as per LCD programming, I want LUT6 in my program. I want the LUT6 for my program. On my, I want to access the LUT6 of my FPGA board. So how the program is to find this LUT in different CLBs. There are many more CLBs is there, of course. Many type of inputs is there, of course. So how they find their perfect LUT for the match in this different kind of LCD? I mean, in the different kind of LUTs, different number of input LUTs. How they found the match of LUT6? So that's my question. Okay. So tomorrow I will explain this one. Okay. Tomorrow we will continue this class. All of you. This is the today class. So thanks for you all. No. FPGA is not like a microprocessor, microcontroller. Yes. So this is the today class. Tomorrow I will explain the backend flow, and of course I will explain the slice-L and slice-M. Okay. The slice-L and slice-M are the internal architecture. It's a very important points. Okay. Yeah. Thank you. If you have any doubts, so please ask me. Otherwise, we will wind up the session.